Okay, let's go ahead and get started here with chapter 4, section 1. All right, factoring whole numbers. This is what this is about. We're going to talk about in first part here this thing called divisibility rules. Now, these are actually really handy, especially in algebra. There's a lot of factoring. There's a whole unit, a whole chapter that covers factoring, and factoring is a pretty big part of algebra just because of a lot of times you have to factor out a GCF or maybe the least common multiple. And those are, you want to know how to do that. And you have to have some idea of what factors mean when you're getting into that unit. Anyhow, with divisibility rules, we're going to talk about some, I mean, there's divisibility rules for lots and lots of numbers. We're going to talk about specific rules just for a few numbers here. These are pretty important numbers though, that you should know the rules for. So let's kind of talk about what a factor is. So a number is considered divisible, all right? A number is considered divisible by another number if one number can be divided or factored, that's the word we can use there, divided evenly with a remainder of 0. That means you can divide it evenly, whether you're dividing it on paper or with a calculator. And you don't get anything left over. You don't get a decimal. You don't get a repeating decimal. You don't get like 0.8. That's it. It divides evenly. So divisibility rules for 2, 3, and 5. Let's talk about those specifically. So the rule for 2, the rule for 2 is pretty simple. The last digit, the final digit, is a 0, 2, 4, 6, or 8. Basically, the last digit is an even number. Okay, so it doesn't matter what all the other digits are. It doesn't matter. So it could be all odd digits. 5, 7, 3, 1. 9, and then it ends in a 6. All that matters is that last digit. Therefore, it's an even number that's divisible by 2. All right, that's a very easy rule. I bet you already knew that. All right. The rule for 3 is the sum of the digits. That means when you add them up, okay, the sum of the digits is divisible by 3. Okay. And then for 5, and we'll get to that rule for 3 in just a moment. And the rule for 5 is the last digit, kind of like the rule for 2, but the final digit is a 0 or 5. Okay? So that's how 5s work, right? We list out the 5s. 5, 10, 15, 20. And list this out forever. 35, 40, 45, etc. Right? You'll notice just from that very short list right here, it only ends in a 0 or a 5. 0, 5, 0, 5. It does not end in anything else but a 0 or a 5. Okay, so determine if the number is divisible by 2, 3, or 5. All right, so for 2, definitely not, because it ends in an odd digit. So not 2. So we can say no to 2. I'm just going to write 2 and just put an X through it. No. All right, now for 3, what you want to do, the rule for 3 is you add up the digits. You take the digits, 8 plus 1 plus 3. Add them up. 8 plus 1 is 9. 9 plus 3 is 12. All right, now does 12 divide by 3 evenly? Yeah, it does. It does. So 3 is a number that is divisible. Okay, so 3 works. All right, and we can definitely say that 5 is not divisible because it does not end this digit. It's not a 0 and it's not a 5. All right, so this next one right here, all right, for B, all right, definitely is divisible by 2 because the last digit is an even number. All right, let's go ahead and just get 5 out of the way as well because it ends in a 0. All right, now let's check for 3. So add up the digits. 1 plus 5 plus 6 plus 0. You literally just add up the digits. It's a weird rule. It's kind of a cool rule that works. 1 plus 5 is 6, and 6 plus 6 is 12. And 12, just like on the last one, 12 divided by 3. So, yeah, all those digits, all those numbers are divisible into 1,560. All right, and then 2022, that is divisible by 2, okay, because it ends in an even digit. It is not divisible by 5. All right, and then if you add up all the digits, 2 plus 0 plus 2 plus 2, that is 6, which is divisible by 3. Okay, so there you go. And you could also, you could always just divide the numbers by 2 or divide it by 5 or 3 and see what you get. But divisibility rules are made to kind of be a quick check, kind of almost like a shortcut where you can just easily, in many cases, just look at the numbers and go, oh yeah, it ends in this digit, it's divisible. Or I can add up these numbers really quick. I can see it's divisible by 3. All right. Identifying prime and composite numbers for the next part here. Okay. So a prime number, let's talk about that. A prime number has only 2 factors, 1 and itself. That's it. So prime numbers, like the only number that divides into 5 is 1 and 5, right? It's only, if I were to write out the factors, it's only divisible by 1 and 5, right? 7 is prime. It's only divisible by 1 and 7. I cannot think of another multiplication problem that makes 7, but we can think of one that has perhaps decimals in it, but that doesn't count. It's got to be, factors have to be whole numbers. They have to be integers, they cannot be decimals or mixed numbers or fractions, right? So 7, prime numbers, like if we were to list out prime numbers, let me just say this before we list them out. 1 is not a prime number because 1 only has 1 factor, okay? So 1 is not a prime. Okay, so prime numbers, I'm going to list out a bunch. So 2 is a prime number, 3 is a prime number, 5 is, 7, 8, 9 is not, 10 is not, 11 is, 13 is, 17 is, 19, 23, 29, 31, 37, 41, 47, 53, 59, 61, 60, 67, and they just keep going, right? But that's like, I went far beyond what I needed to there. But yeah, the prime numbers go on. They are infinite. They definitely get further and further apart as you kind of go on, through all the numbers. But there's an infinite number of prime numbers. Okay. A composite number. So if it's not prime, it's composite, most likely. A composite number has 2 or more factors, okay? Like the number, like when I factor numbers, I like to use a T table, like where I just set up a T, and like if I take 6, for instance, 6 has 1 in itself as a factor pair. I like to start with 1 and then work my way up. So 2 times 3 is a factor pair. So 6 has 4 factors, right? 12. If I list out the factors of 12, it's got 1 and 12. It's got 2 and 6, 3 and 4, right? Definitely more than 2, right? Prime number only has 2. That's it. No more, no less. Just 2. All right. The number 25 has 1 in itself, and it has 5 times 5. So that actually has 3 factors, right? It has 4. It has, if you think about it, it has 2 pairs, but it has 3 factors. Okay, 36 is a composite number. That has lots of factors. Well, not a ton, but that's 1 in 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. Okay, so these are just just a few of many, many, many examples of prime numbers, or composite numbers, sorry. And divisibility rules come into play. Like with 48, I'm just thinking of this. So 1 times 48 makes 48. Yeah, 1 times 48. Got 2 times 24 because it ends in an even digit, right? We know 2 works. We know 3 is divisible because 4 plus 8 is 12. So it's 3 times 16. All right, 4 times 12 is 48. 5 does not work because it doesn't end in a 0 or a 5. 6 works. 6 times 8. All right, and the only number in between 6 and 8 is 7, and 7 is not a factor. Okay, so those are just a few examples of composite numbers. All right. Okay, so the next part right here, we've got, for this part, we got factor pairs, or I'll just say factors. Factors are numbers that are multiplied together. I think I talked about that in an earlier section, but factors are multiplied together. You know, there are lots and lots of examples, like, 4 times 8. Those are factors of 32, right? 9 times 5, those are factors of 45, right? Those are, lots and lots of examples of that. All right. Now that leads into this, which are prime factors. All right. Prime factors are factors that are only prime numbers. Almost sounds self-explanatory. Okay. Find the prime factors of any number by using factor trees, which is my preferred method of doing it, or there's another way to do it, which is division ladders. And there's other ways to do it too. These are probably the two most common ways of finding prime factors. Okay, so let's talk about division ladders first. Now, on division ladders, you continually divide by prime numbers until the only factor is 1. Okay, now what we're going to do, it's kind of weird. We're going to start with, let's say we want to figure out the prime factors of 72. Okay, so 72. What you want to do, and I've got a lot of arrows here, you start by dividing by the lowest possible prime number. So we're going to start with that, dividing by the lowest prime number. So the lowest prime number is 2. Okay, 2 is a prime number. Okay, and 1 is not a prime number, nor is it composite. It's neither, right? So don't start with a 1. It's a bad number to start with. All right, and then you just, and it's kind of like this, like they're called division ladders because it kind of looks like the rungs of a ladder, and so 72 divided by 2 is, and we typically put the number underneath, but we're going to put the quotient, or put what it divides out into on top. So you get 36. 72 divided by 2 is 36. So we put that there. All right, and then you just keep going. All right, and I would just keep using 2 until you can no longer use 2. All right, so 2 divides into 36. Now 36 divides into 2 18 times. All right, so I'm going to put an 18 there. All right, you can see how this is working out. So then I'm going to keep going. We can use 2 again. So 2 divides into 18 9 times. All right, and now we can't use 2 anymore. So now we can use 3. You kind of work your way up. So if 2 doesn't work, try 3. If 3 doesn't work, try the next prime, 5. And then try 7. And then try 11, So we're going to try 3 at this point. And 3 divides into 9 3 times. Okay. So you got that. All right. So we got yeah. And so there we go. So what do we have here? So the where do I put it? I can put it right here. So what you do now, because I want to make sense of this. Now what we do is we take all these numbers that we got. We got 3 2s. We got 3 2s, and then we also have a couple 3s here. Okay, and so those are prime factors. So we can write our answer a couple different ways. We can write our prime factors as just kind of like this, like 2 times 2 times 2 times 3 times 3. All right, we can write it like that, or we can write it in exponent form, which is we can write 2 to the third power times 3 squared. Either way, it's fine. But that's called the prime factorization, what we just did there. All right, that's called prime factorization. All right, and you start with the lowest prime, and you work your way through it until you have no more primes left. All right, so use division ladders to express as a product of prime factors. Okay, so let's do that. All right, so we're going to start with 42, and so we'll start with 2, and then 2 divides into 42. How many times? 21, right? We get 21, so we put 21 here, and then we can't use 2 now, but we can use a 3, so we'll put a 3 here, and then 3 divides into 21 7 times, right? And then I'm going to stop there because the only number that divides into 7 is 1, right? And I didn't say that above, but yeah, the only thing that divides into 3 is 3 or 1, I guess. You can put it like that. But yeah, that's it. So the prime factorization is 2, 3, and 7. That's what it is. So I can just write that out as a product of primes. So 2 times 3 times 7. Those are only, right? Those are only prime numbers. Okay? The 2, the 3, and the 7. Those are only primes. All right? Don't get too concerned if it's a big number like 200. They don't go on forever, but sometimes people get intimidated by that. But let's start with 200, and we'll start with 2. And then that's 100, right? And then keep going. And then what goes in 100? 2 again. All right, and then that makes 50. All right, what goes into 50? 2. Okay, it's very predictable how this works. All right, what goes into 50? 20, or 2 divides into 50 25 times. And then we can't use 2 anymore, but we can use a 5. Use a 5 here. And then get a 5 here. And then that's it. So all the numbers, the 2s, the 5, and then the number at the very top, those make your prime factors, okay? That's what's going on there. All right, so I'm going to write it in exponent form, 2 to the third power times 5 squared. So those are division ladders, all right? Factor trees kind of look like family trees. So you use branches of factors, prime or composite, to find prime factors. All right, so circle prime. So when you do this, I'll kind of demonstrate this, but circle prime numbers. I'm going to put prime numbers here, not factors. Circle prime numbers. Build another branch if it is composite. If it's a composite number, it can keep branching out. All right, the factors at the end of each branch make up the prime factors. It makes up the prime factorization. It's okay for factor trees to start with no factor pair, because do not use 1 as a factor, because we already talked about that. 1 is neither composite nor prime. All right. I don't know if no factor. You know what I think I meant to put here is it's okay for factor trees to start with any factor pair. Just don't start with 1. All right. Start with any factor pair. So what I mean by that, so 48, we can make a branch here, and we can start it off with 2 and 24. We can start it off like that. All right. Or you can start it off with 3 and 16, because that makes 48. We started off with 4 and 12. That makes 48. We started off with 6 and 8. Okay, so there's lots of different ways. That's the point that you want to kind of get in your head, that factor pairs, that's kind of the nice thing about prime or using factor trees, is that it doesn't matter how you start it. Okay, you can start it any way you want. So, but if it's a prime number, if it's a composite number, it keeps branching. So those are both composites, so they can branch off. All right, 6 is 2 and 3. Now those are both prime numbers, so I'm going to circle those. Prime numbers cannot keep branching off. All right, 8 is 2 and 4. Now the 2 is a prime number. All right, 4 can be turned into 2 and 2. 2 times 2. So every branch is basically a multiplication problem. You notice that? So you see how that, like 2 times 3 makes 6, right? 2 times 4 makes 8. All right, so we're concentrating when we do this, right? We're concentrating on the ends. Those are our prime factors, okay? That's what you want to kind of focus on there. And, all right, write them up. So we got, what do we have here? We got 2, we have 4 2's, 1, 2, 3, 4. So I'm gonna write 2 to the 4th power times 3. I can write it all out in expanded form as well. But that's it. Okay, 48. Again, this is what I was showing you. It doesn't matter how you start it off. Just kind of an example here. We can do 2 and 24, right? So 2 is prime, and then branch off 24. Now 24 is, I can do this. I can do 2 and 12. All right. For 12, we can do what? 2 and 6. All right. For 6, we can do 2 and 3. And the point is that you see that there's the same result. You notice that? So you can notice, like, there's 4 2's, right? There's 4 2's. 1, 2, 3, 4. There's 4 2's there. And then there's a single 3. See that? So the same thing. We get the same result. So 2 to the 4th power times 3. And just to make sure you get it, all right, we can do 48 another way. We can do 48 with 3 and 16, right? So 3 is prime, and then 16 is going to be 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. Same thing again, right? 2 to the 4th times 3. All right, so no matter which way you do it, you end up with a 3 and 4 2's. No matter how it goes, okay? No matter how you start it, how that goes, right? All right, so for this one, use factor trees to express each number as a product of prime factors. So let's do this. Let's do 140 is 14 times 10. We can do that. All right, and then 14 is 2 times 7. Now those are both prime. So I'm going to circle those. 10 is 2 and 5. Those are both prime. 2 and 5. Okay? And we end up with the same thing. So we got 2 squared times 5 times 7. See that? All right, 64. 64 is going to be 2 times 32. All right, 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. Look at that, nothing but 2's. How many 2's do we have there? 6 of them. So we have 2 to the 6th power.